This is the second part of our VHDL tutorial where I'll show you how to implement combinational circuits. If you haven't yet watched the first part of this VHDL tutorial, I highly recommend you pause this video right now and go through that one first, since understanding the concept in this lesson relies heavily on what we covered previously. Let me first remind you about what we discussed in the previous video. We discussed how logic circuits can be divided into two main categories: combinational and sequential circuits. With hardware description languages like VHDL, you can describe and implement either type of logic circuit. In VHDL, you can describe combinational circuits in what we call the concurrent section, while sequential circuits are described in the process statement. In today's video, I'll focus on designing and describing combinational logic circuits using VHDL. To describe combinational circuits in the concurrent section, VHDL provides two signal assignment statements. One is called selected signal assignment, and the other is conditional signal assignment. In this video, I'll focus on selected signal assignment. To illustrate this, I've prepared an example so that you can understand how selected signal assignment works by implementing a simple design. You probably remember the multiplexer block from your logic circuits course. It's a type of combinational circuit in digital logic. Multiplexer have several input signals, one output signal, and a set of control or select lines. Based on the value in the control lines, one of the input signals is connected to the output. For example, in the 4-to-1 multiplexer shown in this figure, we have 4 inputs labeled A, B, C, and D, and one output labeled F. Since we have 4 inputs, we need 2 control inputs or select lines, which we'll call S0 and S1. Depending on the binary value on these control inputs, one of the inputs connects to the output. In the truth table for this multiplexer, you can see that when S0 and S1 are both 0, input A is routed to output F. When the control input value is 1, input B goes to F. When it's 2, input C connects to F, and when it's 3, input D connects to F. Now let's see how we can describe this multiplexer in VHDL using the selected signal assignment construct. As I explained in previous videos, in VHDL we use two main parts to define a module. The first part is the entity, where we specify input and output ports, and the second part is the architecture, where we describe the actual circuit. There is also an initial section where we include the IEEE library. This library contains the standard definitions and constructs used in VHDL coding, so it's essential to start every VHDL code with the line library IEEE. This loads the IEEE library, which itself is made up of several packages, some of which are very commonly used. One of these packages that you must always call at the beginning of your code is the stdlogic 1164 package. To include it, use the keyword use, followed by the library name IEEE, a dot, and then the package name. To access all the features of this package, end the line with all. To describe the multiplexer, as I mentioned, the first step is to define the inputs and outputs using the entity section. Since this is a 4-to-1 multiplexer, we define 4 inputs, A, B, C, and D. Here we set their mode to input and their type to stdlogic. For the output, which we'll name F, we set its mode to output, and since it's a single bit signal, we use stdlogic as well. Now regarding the control signal S, since it's a 2-bit signal, we have two options. One is to define 2 single-bit signals using stdlogic type, and the second approach is what you see in this code. Instead of using 2 single-bit signals, I'm using one 2-bit signal. To define a 2-bit signal, we use a type called std logic vector. Std logic vector is used whenever we need to define signals with more than 1 bit. To declare such a signal, we write std logic vector and specify the bit widths. For example, since we need a 2-bit signal here, we define it as std logic vector 1 down to 0. This line means we are creating a 2-bit signal with indices 1 and 0. Now, as I mentioned, to define a 4-to-1 multiplexer with the selected signal assignment statement, we use a specific format as shown in the code. The statement begins with the keyword with, followed by the signal we want to base our conditions on. In our case, this is the signal S. Next, we use the keyword select. Next, we specify that signal A should be assigned to signal F when 0, 0. Now, what does 0, 0 mean here? It means when the condition signal, which is S in this case, equals 0, 0. In other words, when the control input signal S is 0, 0, input A should be assigned to output F. Next, we assign B to F when 0, 1, meaning that when S equals 0, 1, input B is passed to the output. Then we assign C to F when 1, 0, and finally, we specify that D should be assigned to F for any other values of S using the term when others. When others covers all the remaining cases. Once we've written the code, we can check it for syntax errors to ensure everything is correct. To do this, simply click on the code file and at the bottom in the processes section, double-click on check syntax. The ISC software will then analyze the code to confirm that there are no syntax issues. If the syntax check completes successfully, you'll see a message that says syntax check completed successfully. If there is an error, it will be displayed at the bottom of the screen, allowing you to review each error one by one and see how to resolve them. To help you become more familiar with the selected signal assignment statement and learn some additional coding tips along the way, let's modify our multiplexer example a bit. In this version, in addition to the control inputs S0 and S1, we'll add a new control input called enable signal, which will denote as EN in the code. According to the truth table, if the enable signal is set to 1, the multiplexer functions as before. That is, based on the value of S, one of the inputs A through D is connected to the output. But if enable is 0, regardless of the values of S0 and S1, the output signal is set to 0. Now let's see how we can implement this circuit using the selected signal assignment construct. The first part of the code, the entity section, doesn't change much except that we now add the enable signal. This signal is a single bit, so we define it with the type std logic. Now, the main difference in this code compared to the previous one is that for selecting the output signal, we now need both the S signal and the enable signal to work together. However, the selected signal assignment only allows one signal to be used for selection. So what do you think is the solution? To address this, you can define an internal signal and assign both S and EN signals to it, then use that signal as the select signal in the selected signal assignment. To do this, we need to introduce a new operator. So before diving into the code, let me explain this operator. In VHDL, there is a very useful operator called the concatenation operator, represented by the ampersand symbol. To get familiar with this operator, imagine we've defined two signals A and B. Signal A is 3 bits wide and signal B is 5 bits wide. To explain this example clearly, we've labeled the bits of signal A as A0, A1, and A2, and the bits of signal B as B0 through B4. If we use the assignment C is assigned A ampersand B, the value assigned to signal C will be the combination of B0 through B4 followed by A0 through A2. In other words, signals A and B are concatenated into signal C. When using this concatenation, you must ensure that the width of the signal on the left side of the assignment, in this case C, matches the total width of the signals being combined on the right. So if A is 3 bits wide and B is 5 bits, C needs to be 8 bits wide. By using the concatenation operator, you can combine multiple signals and assign them to a new signal. Now let's apply this concept to combine the two control signals S and enable into a single signal that we can use in the selected signal assignment construct. To do this, we first define an internal signal within the Fpga. In VHDL, as I mentioned in the previous tutorial, we define signals in the declarative region, which is the area between the keyword architecture and the keyword begin. This is where we can declare signals and modules. To declare this internal signal, we use the keyword signal followed by the signal name, which we'll call sen, since it will combine the signals S and enable. After a colon, we specify the signal type. Since we're combining a single bit signal with a 2-bit signal, we end up with a 3-bit signal. So we use the type std logic vector and define the widths as 3 bits from 2 down to 0. When defining a signal, you can also assign an initial value. To do this, use the symbol := and specify the initial value in quotation marks. Here we'll set the initial value of the signal to 0. After the begin keyword in the architecture section, where we describe the circuit in the concurrent section, we concatenate the enable signal and the S signal using the concatenation operator and assign the result to the internal signal SEN. This makes SEN a 3-bit signal where the least significant bit is enable and the two most significant bits are S. Now in the selected signal assignment construct, which as I mentioned can only have one condition signal, I can use signal SEN knowing that SEN effectively incorporates both S and enable. Now to rewrite the conditions, we specify that input A is assigned to F when 001, meaning if SEN is equal to 001. You know that the least significant bit corresponds to enable. So it means that if enable equals 1 and if S equals 00, assign A to the output. If enable is 1 and S is 01, B is assigned to F, and so on until we reach the condition where enable is 1 and S is 1, which would assign D to F. So we covered all possible cases where enable equals 1. For other cases, that is when enable is 0, the value of the control signal S doesn't matter to us. So we write when others, meaning when enable equals 0, assign a value of 0 to the output. We are doing this according to the definition we had for the enable control input in our 4-to-1 multiplexer. Now keep in mind that when you're assigning a value to a signal, if it's a single bit value, you enclose it in single quotation marks. And if it's a multi-bit value, you enclose it in double quotation marks. So this is how we describe the code for a 4-to-1 multiplexer with an enable input signal using VHDL. In upcoming tutorials, I'll introduce additional constructs in VHDL that allow us to describe other types of digital circuits. So that's it for today's video. If you found this video useful, please go ahead and hit the like button. Also hit the bell icon to be notified whenever I release a new video. Thanks for joining me. I'm Ahmed Sagafi, and I see you next time.